In this video we're going to convert our MOSFET large signal model into small signal models. We need to add one detail to our large signal model to make that conversion, and that detail is called channel length modulation. When we did our analysis of MOSFET current and saturation, we assumed the channel length wasn't changed by pinch-off, but really our channel doesn't reach all the way to L. It instead reaches to some shorter distance L minus delta L, where delta L is the size of the pinched off region. And it's worth noting that delta L changes a little bit as VDS changes. So I've included that correction by replacing L in this expression with L minus delta L. Alright, so that delta L factor is annoying, and so I've factored our equation to make it a little less annoying. On the left we see the same current expression for a MOSFET and saturation that we had on the previous slide, and on the right we have some correction factor that accounts for delta L. And one thing that we know for sure is that this delta L over L in the bottom of our expression is small, because the pinched off region is a small portion of the channel. That means we can just linearize this using a binomial expansion. And so we convert this function of VDS that's small into VDS multiplied by some coefficient lambda. And it's worth noting that this term over here looks a lot like the correction that we added to BJTs to account for base length modulation. So lambda has some sort of relationship with an early voltage, probably. And in fact, that's part of its definition. Lambda is 1 over the early voltage for MOSFETs. You can also calculate it directly if you know exactly how delta L changes with VDS, but that's pretty hard to predict and tends to be extracted experimentally. Okay, so as usual we're going to be taking a bunch of derivatives to find our small signal value dependences on different voltages. And I'll be filling out those relationships on our small signal model down here as we find them. Now we can get a quick start on that process by noting that we already have the gate to source element and the gate to drain elements perfectly correct, because we remember that the gate had a big oxide underneath it, so approximately zero current ran through it. And so just leaving open sources in our small signal model is an accurate representation of how the gate is connected to the drain and the source. Noting that, we're going to continue finding elements that do connect these terminals by ignoring the channel length modulation to start with. And that'll let us find the drain current dependence on gate source voltage, which tends to be much bigger than the drain current dependence on drain source voltage. So I've included our expression for current and saturation here as a reminder, and we take a derivative of it with respect to VGS and evaluate it at our bias point. We'll call this GM because this is how the drain current changes when we move the gate voltage, so it'll be a transconductance. And that derivative is pretty easy to evaluate. This is a polynomial, so we just pull this 2 down in front, and we're left with mu n Cox W over L times VGS minus VT. So this is a perfectly reasonable relationship that shows that GM is linearly related to the overdrive. That's all cool, except this constant is kind of a pain. So in the past we were able to get rid of these sort of painful constants by rewriting our small signal parameters in terms of the bias current. And I've done that here, which involved sort of inverting this equation to write overdrive in terms of ID. But we still have the mu n Cox W over L coefficient in our equation, which is annoying, though it's neat to note that GM depends on the square root of ID. Fortunately, we can find an expression for GM that makes our life easier. I've started with our GM expression from the left column, and then in the second step here I've multiplied by the overdrive divided by the overdrive. So one factor of the overdrive got absorbed in here, and we have 1 over the overdrive over there to make sure things stay calculated correctly. This is promising because this looks almost like our drain current. So in fact, if we substitute in our drain current into this expression, we're left with this much nicer looking equation, which says that GM is equal to 2ID over the overdrive. This expression is a little bit redundant because ID and overdrive are one-to-one functions of each other. They're just directly related by this equation. But it's handy because it's simple enough that you can remember it and you don't need to remember any constants that change with your MOSFET. But regardless of which expression we use, this derivative indicates that VGS changes IDS, and because a voltage at one place affects a current somewhere else, we represent this behavior as a dependent current source that connects the drain and the source node, and that's controlled by the voltage across the gate in the source node. We add channel length modulation back in to find how our drain current varies with VDS, and that's because there'd be no VDS dependence if we ignored channel length modulation. So taking a derivative of this modified ID equation with respect to VDS and evaluating it at our bias point, we observe that's going to be equal to 1 over our output resistance, 1 over RO, and also that it's a pretty easy derivative. There's only one VDS term in here, and it's just a linear value. So we're left with lambda times whatever this big coefficient is. And this big coefficient happens to be equal to ID. So 1 over RO is equal to lambda ID. That looks like an output resistance, so we add RO between the drain and the source. And with that, we've covered all of the components that are needed to represent small signal models for this equation, the one that we started with. So this is the small signal representation that you use most of the time. Awesome. However, it's worth noting that there's one additional component we can add to capture the effect of the body being at a different voltage than the source. The body effect creates another GM generator that depends on VBS. And this GM generator is sometimes called the backgate effect because the generator over here has the same effect on the small signal model as moving the gate around. So in summary, remember that we find small signal models by taking derivatives of current with respect to each control voltage, and we represent those as resistors or transconductances depending on the units of our derivative and the terminals that we're hooked up to. For a MOSFET, there's no current into the gate, and our small signal model is summarized down here. It's a GM generator between drain and source, an output resistance between drain and source, and RO is given by 1 over lambda ID, and GM is given by 2ID over the overdrive.